Okay, and thanks very much for agreeing to give the talk. So we're pleased to have Gabor Lugosi, who's going to talk about learning the structure of graphical models by covariance queries. Thanks very much.
Yeah, thanks for inviting me. I wish next time, hopefully it will be in person. So yeah, this talk is about graphical models, and I don't know how many of you know about graphical models, but if you don't, then you are like me when a couple of years ago when we started this project. So this was completely a new area for me, but I think it's pretty exciting. And I have this colleague Piotr. Who is an expert, and then we started brainstorming, and then this is what came out. So the and the other co-authors are Jakub Truszkowski and then Vasiliki Velona. She's now a postdoc. She was a student at that time. Okay, so the motivation is Gaussian graphical models. I will tell you what this is and where the motivation comes from, but then the mathematical problem we ended up solving actually is motivated by this, but it has nothing to do with Gaussian vectors and stuff like that. I will explain what I mean by this. So what are these graphical models? So if you have a high dimensional, let's say Gaussian vectors, but graphical models are also exist for binary vectors and for other types of distributions. But for Gaussians, things are really nice. So if you have a high dimensional multivariate Gaussian vector, and think about n as 100,000 or a million, something really big. So that was our main motivation. That has some covariance matrix. Then the inverse covariance matrix, that in this literature sometimes they call it a precision matrix or concentration matrix, has this really fascinating property that whenever an entry of the inverse covariance matrix is 0, that means that the corresponding two entries, the corresponding two components, xi and xj, are conditionally independent given the rest of the variables. Okay, so the zeros in the inverse covariance matrix have this really nice interpretation. Okay, and and based on this, this means that whenever we have a non-zero entry, that means that those variables are somehow related, even conditionally not independent, given the rest of the variables. So this this motivates the definition of what's called a concentration graph, where we just throw a graph whose vertex set is just the integers from 1 to n. So the vertices correspond to components of this matrix, and then we draw an edge. We connect vertex I with vertex j whenever the corresponding entry of the inverse covariance matrix is not 0. Okay, so the absence of an edge means that those two variables are conditionally independent given the rest of the variables. Okay, so here's a little picture. So let's say we have a 9-dimensional Gaussian vector whose covariance matrix. Let's say 0 mean that's not interesting. That's not important for this talk. So we may assume that it's a 0 mean random variable, random vector with inverse covariance matrix k. So when there is no edge in this graph, this green the green edges, these green lines are the edges in the in this graph. So whenever there's no edge between two variables, so for example, there's no edge between vertex 2 and vertex 9, that means that vertex 2 and vertex 9 are conditionally independent given the rest of the variables. Okay, and there are also very nice other nice properties. For example, if we have a set of vertices, for example 5 and 9, that separate two sets of vertices, right? So for example, this 5 and 9 separates 1, 4, 9 from 3, 6, 2, and 8. Okay, so what this means is that every path going from any vertex in this set between 1, 4, and 9 to any other vertex between 3 and 6 must go through one of these things. Okay, so that's a separator. So when we have a separator, that means that that these two sets of variables, x1, x4, x7, and x2, x3, x6, and x8 are conditionally independent given x5 and x9. Okay, so there are all these nice conditional independence relationships encoded in this precision graph or concentration graph, or what this is called the graphical model. Okay, so so since this graph has and another very nice property that's important in applications is, for example, if I want to find the best prediction of x8 given the rest of the variables, so if I want to do regression on 8 based on the other variables, then the optimal regression function is only a function of the neighbors of 8. So it will be a function of 2, 3, and 5. Okay, so of course this makes statistical inference much easier, and because of this in machine learning, graphical models have been really useful, and then they have been studied a great deal in for many years now. Okay, and in particular, finding the structure, finding this graph, estimating this graph in some sense has been in the center of attention. So this is the structured learning problem. Okay, so we would like to learn the underlying graph when we have a really high dimensional Gaussian, let's say Gaussian vector. Okay, so in this huge literature that I'm not going to survey, because that would take much more than all the time that we have. So in this literature, the focus is to find methods that recover this graph based on as few samples of this Gaussian vector as possible and as fast as possible. So sample and time complexity are both important. Okay, but all the algorithms. So the typical setup is that we have independent observations of this Gaussian vector. Okay, and then we would, based on that, we would like to estimate this underlying graph. Now all algorithms, all of them, start by computing the sample covariance matrix. So everything is based on the sample covariance matrix. The problem is that when n is 1 million, then the sample covariance matrix is a 1,000,000 by 1,000,000 matrix, and such examples really exist. So in mostly in biology, where you want to recover phylogenetic trees and stuff like that, this n can be really large. So even writing down the covariance matrix is already prohibitive. So just the first step of all the algorithms is already too expensive. So the question that we asked here is that, is it possible to recover this graph with less than quadratic complexity? Okay, so we are not allowed to write down the sample covariance matrix. Okay, now clearly this question is only meaningful if this graph is sparse. If the underlying graph is dense, then just writing down the graph already takes a quadratic number of quadratic time. So we have to assume that the graph is sparse, but all the algorithm, this is always the focus of the research, that the graphs tend to be sparse, otherwise they are not interesting. And
can I ask a question? A silly question.
Of course.
So this property about the conditional dependence, it's only for Gaussian, for the Gaussian distribution.
This is for the Gaussian. It's also true in some form for some other distributions. So for binary variables, there are whole books written on this.
It doesn't hold for any exponential family.
It doesn't hold for exponential families. No. But yeah, but on the other hand, yeah, and maybe I should have said this. So even if x is not Gaussian, if it's an arbitrary vector, this matrix, this graph is interesting because if you want to know what's the best linear regression function of 8, given all the other random variables, then it is true that that it's just the neighbors of this graph. Okay, so if you only want to do linear regression, then graphical models are useful no matter what. Okay, so of course for Gaussians, the best regression function is linear. So okay. So of course this whole question of trying to find the structure in a subquadratic time is only meaningful if the graph already has a subquadratic number of edges. So it has to be sparse. So here's the model that we introduced to study this problem. So and now we will forget the Gaussian motivation. This is really just, if you wish, a computational algebra question. So suppose that we have a symmetric positive definite matrix. So this would correspond to the covariance matrix of the Gaussians. Okay, and then we can define the graph G of sigma, which is just the graph that's induced by the non-zero entries of the inverse covariance matrix. Okay, so this is symmetric positive definite. It has an inverse, and then we look at where the zeros of these entries are, and if the non-zeros are sparse, then this question will be meaningful. Okay, so G of sigma is the graph that we want to find out, and now what we are allowed to access is what we call a covariance oracle. So what we can do at each step of the algorithm, we can query elements of this matrix. Okay, so the types of type of questions that we can ask this oracle is that what is the covariance between variable I and variable j? Okay, so that would be the statistical statistical application. Okay, so we can always ask the oracle entries of this matrix, and now what we would like to do is to learn the support of the inverse of this matrix with as few oracle queries as possible. Okay, please interrupt me if the question is unclear. Okay, so the algorithm that we are allowed to use at each step of the algorithm can ask questions of, please tell me what's the entry of this matrix at, let's say, row 500 and column 59. Okay, so these are the types of questions, and we would like to ask as few questions as possible. In particular, we would like to, of course, if we ask all the entries of this matrix, then we know the matrix. We can just invert the matrix, and that's it, and then we have it. But of course, both the oracle complexity, the number of times we ask this oracle, would be quadratic, and the computational complexity would be even bigger, because inverting the matrix it takes more than quadratic number of steps. Okay, so we would like yes.
How will you choose a pair IJ?
I will explain. Okay, so that we would like to design algorithms that are adaptive. Okay, so we start asking questions as we learn things, then we will adaptively ask these entries, and hopefully after a small number, subquadratic number of questions, we will be able to determine the inverse, the graph. Okay.
Okay. Thanks.
All right. So more general, the inverse covariance matrix is the entries of the inverse covariance matrix are sometimes called partial correlations. Okay. All right. So the question this is the topic of this talk is, under what conditions is it possible to recover the graph with just little O of n squared queries? Okay. Now here's an easy counterexample. Suppose that all the variables are independent. Okay. And except maybe two of them are dependent. Okay, so that means that the graph consists of just one edge. Okay. Now, clearly, in this case, if we ask queries, we will get just the oracle will just give us 0, 0, 0. Everything is independent. So in order to recover that graph that only has one edge, we actually have to hit that edge. So there's no hope to do anything. So if the graph is in particular, if the graph is not connected, then we have a problem. But of course, in practice, things are connected, right? Because the graph is connected because the variables are dependent somehow. So we will assume that this graph is actually connected. Okay. And now I will start with the discussing the simplest possible connected graphs, that are trees. Okay. And in fact, trees are important for a number of applications. You can think about phylogenetic trees, right? Which are examples of graphical models. All right. Okay. Now, for trees, we have this beautiful algebraic property that says that if the underlying graphical model is a tree, meaning that the graph defined by the non-zero entries of the inverse of this positive definite matrix is a tree, then the correlation is just the normalized covariance. The correlation between vertex I and vertex j is just the product of the correlations of the unique on the unique path between these two vertices. Okay, so if the underlying graph is a tree, then for any two vertices there's a unique path that connects two vertices, and the correlation between these two vertices will be just the product of the correlations on all the pairs.
I'm sorry, I believe there is a notational confusion. It's like sigma, because I think in the denominator and numerator of this formula, in one case, sigma is used as a standard deviation, and in another case, it's used as the element of sigma.
You're totally right. You're totally right. Yes, absolutely. Yes, there should be either a square here or a square root.
Okay.
Yeah. Yes. Thank you. Thank you. These are the usual correlations. So we have this really nice property that the correlations are products. So what this means, what this implies, is that that the tree is nothing but the maximum weight spanning tree. Okay. This is a well-known fact, and this famous algorithm of Chu and Liu, dating back to '69, uses this to recover the underlying tree. Okay, so we can now use maximum weight spanning tree algorithms to find the underlying tree. But of course, to run this algorithm to find the minimum spanning tree in a graph, all the correlations must be known. Okay, so that's quadratic complexity. So in order to overcome this, we propose a divide and conquer type algorithm. Okay, so this is going to be a randomized algorithm where our goal is to suppose that we can find a central vertex. So what does central vertex mean? It means that by removing that vertex, the tree decomposes into small pieces. Okay, so if we could somehow find the central vertex, then and we could identify these the little subtrees that hang off this vertex, then we could recurse, right? We have this nice property that the graph, if we restrict our attention to this subset of vertices, then the underlying graphical model, the underlying graph, is exactly this tree, which is exactly this graph, which is just a subtree. So, and therefore we could just go down and try to find. And now we have much smaller subproblems, and in particular, if we can guarantee that all these subtrees are a constant factor smaller than the entire tree, then in a logarithmic number of steps we could be done. Okay, so how do we find the central vertex, and how do we identify these components? That's the question. Okay, so the centroid of a tree is every tree has a centroid, one or two centroids. So every tree has one or at most two vertices that have the property that by removing them, the tree decomposes into subtrees of size at most n half. Okay, so that's called the centroid of the tree. Now that would be the best, right? Because if you could find the centroid of the tree, then all subtrees would have size at most half of the entire tree. But unfortunately, we don't know how to find the centroid. However, right, so the centroid is just the vertex that minimizes the maximum, the size of the biggest subtree. Okay, so for a vertex, right, for this vertex, we have these subtrees, right, and the centroid is the one that minimizes the largest of these guys, right? For example, if we have a leaf, then there's one subtree that contains almost all vertices except for this one. So that would be a very large subtree. But in the center, if we remove a vertex, then all subtrees will be small. So this is the centroid. But we don't know how to estimate this quantity. However, we can modify. If we replace this maximum by a sum of the squares of the sizes of these subtrees, then this is a quantity that we can very quickly estimate. And so here's what we do. We fix a vertex. So we will do this for every vertex, okay? But there's only a linear number of vertices, and the work that we do is only going to be logarithmic, okay? So this is going to be cheap. So for every vertex, we will try to estimate this quantity. And how do we do that? We pick k vertices at random, completely at random, okay? So we fix a vertex, for example, this, and then we pick a few vertices. Now, you see, because of this product property, if we have, for example, this vertex here and this vertex here, then we can decide whether they are in the same subtree or in a different subtree, right? Because if they are in different subtrees, that it means that the vertex that we chose, our pivotal vertex, is on the path between these two vertices, and therefore the correlations have this product property, right? The correlation between this vertex and this vertex will be the product of the correlation between this vertex and this, and the correlation between this vertex and this vertex. Okay. Whereas if I pick two vertices that are in the same subtree, let's say this one and this one, then this is not true anymore. Okay. So for any two vertices, with just 3 queries to the covariance oracle, I can decide whether they are in the same subtree or not. Okay. So so we can just count, right? If our vertex was very central, then this random sampling will be a sufficiently good approximation, right? We can very quickly estimate if they estimate this quantity. Okay, so in particular, one can show that the vertex that optimizes this. Okay, so we just take we do this. We pick k vertices at random, and then now for each vertex we can estimate its centrality according to this measure. Then this vertex has a centrality according to this measure. Okay, so the size of the largest subtree hanging off this chosen vertex is at most 96% of the size of the whole one. Okay, so the square root of 11/12. This is the important thing, that this is a constant which is smaller than 1. Okay, and this can be achieved whenever k is logarithmic in n. Okay, and this step only requires order k times n queries, because for each vertex we pick k random vertices and then do this estimation. Okay, now. So this means that we can find a central vertex. Now the next step is that we have to identify which vertex belongs to which subtree of this. But again, this can be done quickly if the maximum degree of the tree is not too big. Okay, so if the maximum degree in this tree is at most d, then one may identify the components of all these subtrees using just order d times n queries. Okay, so now it's based on this. It's really easy to see that we can actually identify the underlying tree in at most this many steps. So what's this? So n log n. That's great. Remember, we want something which is smaller than n squared. So n log n would be fantastic. Then there's another log n here. that's okay. That's also good. Epsilon is the probability of error. So the probability of error this algorithm will find the tree deterministically. This probability means that with probability 1 minus epsilon, it finds it in this many steps. Okay, so this is there's the probability that the algorithm will run longer. So that's also only logarithmic dependence. And there's this d times n, okay, which is the maximum degree. Now, of course,
excuse me, I forgot. What's the randomness in CV hat? You say probability CV
okay,
hat.
So V hat is the vertex that we choose by doing this. This is the most central vertex that we.
Okay, I see. So randomness is U1 to UK. Okay.
And that's random because we pick the vertices at random. Okay.
Okay.
Yeah.
And so in this procedure, we know the graph. Yes.
And then we know the graph. Yes. So
no,
after
I mean when we talk about so I'm thinking how do you know it's connected or not?
Oh, so we have to assume that that there are dependencies.
So no. I mean, could you go back to the previous slide?
Yeah.
My question was, oh yeah. So no. Next one.
Next one here.
Next one. So what's known or what's unknown? I get confused again. So you see here the last line. Yeah. So UI, UJ are not separated by V. So what do we know right now? Given UI, UJ, how do I know they are separated or not?
Oh. So yeah, okay. So if I pivot at this vertex, okay,
okay. So right now we know this graph, yes.
No, we don't know the graph. We don't know anything about this.
Okay. Then how do we know?
So I want to estimate the centrality of this vertex. Okay?
Right.
We do this for every vertex, so that's
right.
only linear number. So we look at this vertex, okay, and now I would like to know how big are these subtrees, okay?
Right.
So the way to do it is that I take a random sample of vertices, and now for each pair of vertices, I can use the covariance oracle to determine whether the pivot vertex separates these two, right?
So that requires an algorithm to do it.
So we have to ask the oracle, what's the covariance between this vertex and the pivotal vertex? What's the covariance between this vertex and the pivotal vertex? And what's the covariance between these two vertices? So only 3 questions, okay?
Okay, thank you.
So this is n times k times 3, okay? This is how many times we have to use the oracle to compute this. And then we will have the graph after just n times polylog of n times d steps. Okay.
Polylog comes from comparing all pairs of vertices in a sample, so it's like poly of k.
Right?
It's like k squared.
This, yes.
Just like exactly. It's not kn queries, to be precise, it's k squared and queries, something like that.
K squared.
I mean,
yes. Okay. Yes. Thank you. Okay, now you can ask, is this maximum degree, this is not too nice, right? But in fact, this is necessary, okay? So
another question, just a notation, the capital omega dn, that capital omega means what? Next one, next page.
This is just, in computer, this is just order at least. This means it's lower bounded by d times n, by constant times d times n.
Okay.
Omega is the reverse of big O. So at least constant times dn queries are necessary to recover trees. We can prove this. I'm not gonna show you the proof, just the intuition that, for example, if we have these 2 vertices, this is a star, right? But there's a vertex of degree n minus 1. Here, this is almost a star. It just differs from the star by in one edge. Now, in order to distinguish between these 2, we actually have to query the covariance between the green and the red edges, because any other query, any other information that we get, if we ask what's the covariance of this green with any other vertex, that's not going to give us any information as to whether we are in this situation or in this situation. So, so from this, it's easy to prove that in this particular case, we need at least n squared queries, and you can generalize the argument to show that that if the graph can have a degree has vertices of degree large degree, then no algorithm can work. Okay. But the small degree, the small degree assumption is actually not bad. This happens in most applications. So these trees are somehow nice. Okay, so so now let's move on and try to see how much of this can be generalized to graphs other than trees. Okay. And here we need the notion of bounded tree width. So in graph theory, there's and especially in algorithmic graph theory, this notion of bounded tree width is very important. This is many graphs that have this property can be so many graph algorithms can be designed for graphs with small tree width. Divide and conquer type of algorithms, which would be otherwise NP hard, but for these for graphs with small tree width, there are efficient solutions. Okay, so I'm not going to give you the definition, the precise definition of what tree width is. What's important for us is that graphs with bounded tree width have small separators. Okay, small balance separators. So in trees, the key to this algorithm was that we could find a central vertex. There's always a vertex whose removal results in decomposes the graph into small pieces. Okay, so a balance separator is now a subset of vertices that has the property that if we remove it, then all the connected components will be small. Okay, so if the tree width of the graph is at most k, then it has a separator with of size at most k plus 1, such that all the after removing this set, all the remaining components of the graph will be small, will be at most half of the size of the entire graph. Okay, so these balance separators generalize what we had for trees. For trees, there was just one vertex that we could remove. For graphs with bounded tree width at most k, there's always a subset that we can of size at most k1, whose removal decomposes the graph. Okay, so if we could find a small balance separator, then we could mimic the algorithm before. Okay. The problem is that even if the separators are of size 2, this is much more difficult now, right? Because in the case of the trees, we could just go through every single vertex and estimate how central that vertex is. But now we would have to go through all pairs of vertices, even if we're looking for separators of size 2, or if you're looking if the tree width is 5, then we would have to look for separators of size 6, and there are n to the 6 of them, so that's way over our budget. But luckily, there's this beautiful algebraic property that was proved by these people, Sullivan, Talaska, and Reisman, that has the following property. So it says that that if we have two subsets of vertices, okay, A and B, and we look at the submatrix of the covariance matrix that are indexed by, let's say, the rows are indexed by vertices of A and the columns are indexed by the vertices of B. Okay, then the rank of this matrix is small if and only if there's a small set that separates these two vertices. Okay, so we can look at the rank of the submatrix indexed by these two sets, and if the submatrix has small rank, that means that this happens if and only if there's a small separator. Okay, in other words, the rank of a submatrix is at most the size of the smallest separator. Okay, and here importantly, equality holds for almost all covariance matrices. Okay, so generic means that there is a dense and open set. So it's much more than just a dense subset. It's a dense open set. So there are really very few exceptional matrices when equality doesn't hold.
Sorry, good question.
Yeah.
I think I may be misunderstanding this. So sigma AB is sigma with rows corresponding to vertices A and columns corresponding to vertices B. Right. So it sounds like this is saying if I take two individual points, I can always separate them with just a single point because the rank. Does it make sense? My concern? Yeah. Like this is a. So if A is a single point and B is a single point.
Right.
Oh, okay. It's something about being K tree width tells you this?
Right. No, this is true totally in general. This has nothing to do with tree width.
Okay, wait. So if I have like a fully connected graph. Yeah.
So this. So here you could just take S to be equal to A. Okay. So separator means, here's the definition of what separator means. If any path from A and B contains a vertex. So the separator can be a subset of one set. So the example you're asking is not an interesting one.
You know, I understand that. Sorry, I'm understanding this wrong somehow. I'm just so the rank A, B, if A and B are both single vertices, this is always just a one by one.
That's just one. Right? That's just one, and then there's no contradiction because there exists a set here. You can just take the set to be the vertex in A, okay, and that will separate A from B because it.
Okay, fair enough.
Because it satisfies this, right?
Thank you.
Every path from A and B. So S can be a subset. S doesn't have to be this.
Okay, thank you. Great.
Yeah. Okay. So in particular, we also have this follows that now if we add a subset so AC, this means A union C and B union C. Okay. So this equals the rank of A and B if and only if C is a subset of a minimal separator of A and B. Okay. And this is the property that we will use. So here's how it works. This ladder graph is an example of a graph of treewidth 2. Okay. So here there are separators of size 2. This is a balanced separator of size 2, for example. Okay. And now we're trying to find a small balanced separator. Okay. Unfortunately, we can't exhaustively go through all pairs of vertices and find it. So here's what we do. Similarly to the tree case, we take a random sample of the vertices and m of them. Okay, and this m is going to be logarithmic. Well, it depends on the tree width. But tree width is, think about the tree width as, well, in this case it's 2, but it's a small constant. Okay, 2, 3. They're very complicated graphs. For example, all series parallel graphs have treewidth 2. Okay, so there are examples of complicated graphs that are that have small treewidth. So k is just a constant, and this tilde means that up to logarithmic factors. So this m will be something like k times log n or k times polylog n. Okay, so that's how many vertices we pick. Okay. And now we can exhaustively search through all subsets of this, okay, and find a subset that is a balanced separate. Find a subset in the whole graph that's a balanced separator of the red vertices, okay, of this small random collection. And now we will argue that this is actually a balanced separator of the whole graph. Okay, and all right, so this is what we do. We exhaustively search through all the approximately balanced partitions of the W are these red vertices of this random sample. Okay, so for all partitions of this that are approximately balanced, we find a minimal separator. Okay, we can do this because we can check this rank condition. We can just check each we can add vertices one by one and see if the rank of this thing of this matrix increases or not. If it does not increase, then it means that this vertex is in a minimal separator. Okay, so we can do this greedily, and this will only take linear time. And okay, so that's what we do. And now the key step in the analysis is to argue that if I find a balanced separator of the red vertices, then it will be an approximately balanced separator of the whole graph. And for this, we use VC theory, Vapnik-Chervonenkis theory, which is a theory of uniform convergence of relative frequencies to probabilities. And in particular, we use this nice lemma of Feige and Magdian, who proved that for any graph, if you can define a class of sets of vertices that one can obtain by removing a subset of size k, and looking at so if you remove k vertices, then we look at the connected components. These will be the sets in this class. Okay, so we have a class of sets of vertices that can be obtained like this, removing a set of size at most k, and looking at what are the connected components. Okay. Now the VC dimension of this class of sets is linear in k, is at most 11k. Okay. So this is a really nice property, and this implies, by the standard Vapnik-Chervonenkis inequality, this implies that that in fact, by taking a small random set, any approximately balanced separator of the red points will be also an approximately balanced separator of the entire graph. Okay. So sorry, this is very sketchy. I hope you get something from my explanation. So so once we find a small balanced separator, then we have to determine the connected components. This can be done again quickly using the same algebraic property that I mentioned, the same rank property, and this can be done, yeah, in linear time. And again, we need something like the bounded degree condition. Actually, we don't really need bounded degree. We just need bounded fragmentation, meaning that, by removing a subset of size k, the graph doesn't decompose into too many pieces, but bounded degree is sufficient. Okay. And okay, this is a small technicality that I will skip. One has to be a little bit careful because it's not true what we used for trees. That, remember, when we removed a vertex in the trees, then the graphical model corresponding to the subtrees were also just those trees, so we don't have to worry about anything. But if we remove a separator, then in this subset there may be new dependencies that are added, right? Because this vertex and this vertex may be dependent based, through this path. Okay, so there may be new vertices, but one can take care of this by using a nice property that's well known in the theory of graphical models. One can use conditional covariances, and these can be computed quickly using the covariance query. So so summarizing what
But this is for Gaussian, right?
So the motivation was Gaussian. This is
no, I understand, but this last property with the conditional precision matrix.
No, this is just no. This is just a property of positive definite matrices. Okay, so of course a Gaussian is determined by its covariance matrix. So every property the Gaussian has is just a property of covariance matrices. So this is something that yeah. So in our formulation, we don't need anything about Gaussians. We just work with the covariance matrix. Okay, of course. Yeah, what does conditional covariance matrix conditional covariance mean? Well, that is the analogous notion from the Gaussian case. Okay, but this is just a purely algebraic property. So what we have at the end is that if we have a generic matrix, and you can see that this genericity is sufficient, is necessary. There are exceptional graphs where, for example, you can also think about the tree case when if a correlation equals 1, that means that those are identical. Two variables are equal, and then even we have identifiability problems. So excluding cases like that, which is really they are really exceptional cases. If the graph has, if we know that the underlying graph has treewidth at most k and degree at most d, then both the query complexity and the computational complexity are bounded by something like this. So let's see what we have here. Our main interest was in n. That's what's large. So this is not quadratic, right? It's n times polylog n. There's d coming in. There's the treewidth coming in, and the treewidth comes in a bad way. It's exponential, or even actually worse than exponential. But this is at least exponential is necessary. That's true in all these graph algorithms. All these efficient algorithms actually has a very bad dependence on the treewidth. But again, think about k as it equals 2 or 3 or something very small. Okay, so what's interesting is that we actually with this method we not only find the underlying graph, but we actually invert the matrix. Okay, so what this means is that we can invert an n by n matrix using just n log n, just looking at about n log n entries of the matrix. Okay, so how is this possible? Well, it's possible because we assume that the matrix has this property. The inverse of the matrix has this structure. Okay, so if you have a positive definite matrix such that the inverse has has a support that's supported on a graph of bounded treewidth and bounded degree, then we can invert this matrix just by looking at about n times polylog n of the entries of the matrix. Okay. All right, I'm out of time, but very quickly I would just mention that of course in statistical applications the covariance oracle is never perfect, so it will be noisy, right? So for example, if the covariances are estimated from data, then this is inevitable, and then one can do something, but one has to be again a little bit careful because if, let's say, if the oracle can make an error of size epsilon, then it will be difficult to tell apart the covariances that are equal to 0 from covariances that are small. For example, if our graph is just a long spaghetti, right, just a path, then the covariance on the two extremes will be let's say on the covariance is everywhere 1/2, then the covariance on the two extremes is gonna be 2 to the minus n, is exponentially small. So we need something, we need a condition on the diameter of the graph, or at least epsilon has to be smaller than the accuracy has to be smaller than something that's exponential in the diameter of the tree. This is inevitable. Okay, I will skip the statistical part, and let me just conclude that, that this is where you can read more about this if you're interested.